Figma's been one of the heaviest users of Postgres for a while, and as great as that has been, they've run into a lot of issues because, believe it or not, Postgres by default doesn't scale very well. Postgres is kind of an all-in-one box where the query layer, the storage layer, and all the implementation details are squeezed into one specific package and one way of doing things. And once you have to scale it by like sharding or making hot paths faster or doing all the things you might have to do as your database scales to millions of users and billions of rows, Postgres doesn't have much to help you there. Know that there are other solutions that aren't Postgres that scale better, and we'll be sure to talk about those throughout. But for now, let's focus in on Figma's experience making Postgres scale. How Figma's database team lived to tell the scale. Love a good pun to get started. Here is the 9-month journey that Figma went on to horizontally shard their Postgres stack and the key to unlocking nearly infinite scalability. Vertical partitioning was a relatively easy and very impactful scaling lever that brought us significant runway quickly. It was also a stepping stone on the path to horizontal sharding. If you're not already familiar, they did a blog post like probably a couple of years ago now where they were having so many issues with their single Postgres instance that they had to scale it. Now they've more thoroughly scaled things since. Interesting to see how this has changed over time. We'll probably reference the old article as well. Figma's database stack has grown almost 100 times since 2020. This is a good problem to have because it means our business is expanding, but it also poses some tricky technical challenges. Over the past 4 years, we've made a significant effort to stay ahead of the curve and avoid potential growing pains. In 2020, we were running a single Postgres database hosted on AWS's largest physical instances, and by the end of 2022, we had built out a distributed architecture with caching, read replicas, and a dozen vertically partitioned databases. We split groups of related tables, like Figma files or organizations, into their own vertical partitions, which allowed us to make incremental scaling gains and maintain enough runway to stay ahead of our growth. Really good call out, really good summary, well written. The key point here is that different tables were being separated into their own databases so they could scale that way. So users would be one table, orgs would be one table, apps would be one table, projects would be one table. And by doing that, each one can now scale up itself. And users being huge doesn't mean everything else has to be slow or limited by how many users you have. Really cool stuff. Despite our incremental scaling progress, we always knew that vertical partitioning could only get us so far. Our initial scaling efforts had focused on reducing Postgres CPU utilization. As our fleet grew larger and more heterogeneous, we started to monitor a range of different bottlenecks. We used a combination of historical data and load testing to quantify database scaling limits from the CPU and I/O to table size and rows written. Identifying these limits was crucial to predicting how much runway we had per shard. We could then prioritize scaling problems before they ballooned into major reliability risks. This is the type of stuff you have to do to make Postgres scale. It's kind of insane that you have to custom load test and build your own tools to identify at what level of read-write throughput are we going to start being throttled by the CPU. These things are complex, and I think we can all agree that it's a little bit absurd that you have to be this deep in databases and have like a world-class database team to build an app for designing user interfaces. The fact that Figma needs this level of shit is absurd. And I would argue a failure of database design and infrastructure that even Figma has to care this much about something so far away from what they're building. Like imagine if the average game dev had to care about assembly and like know about the way that DirectX like translated instructions to assembly. It's just absurd that we have to care this much. And I would hope most companies wouldn't have to be this deep in database land just to make sure things don't collapse under load. Ideally, the generic solutions would be outsourced and purchasable in some way, so I wouldn't have to hire a 10 to 20 person team. I could just pay a service an amount of money to make this problem go away for us. And this video is not sponsored, but PlanetScale is still my database of choice for this reason, because they made MySQL scale very well using Vitesse for you with both vertical and horizontal sharding. Call me a shill all you want. There's a reason I like the service, and it keeps me from having to do these types of things. We'll talk more about what that means as we go along. The data they collected revealed that some of their tables, containing several terabytes and billions of rows, were becoming too large for a single DB. At this size, we began to see reliability impact during Postgres vacuums, which are essential breakdown operations that keep Postgres from running out of transaction IDs and breaking down entirely. Our highest write tables were growing so quickly that we would soon exceed the maximum I/O operations per second supported by Amazon's RDS. Vertical partitions couldn't save us here because the smallest unit of a partition is still a single table. To keep our databases from toppling, we needed a bigger lever. Scaffolding for scale. We outlined a number of goals and must-haves to tackle short-term challenges while setting us up for smoother, long-term growth. We aimed to do the following. Minimize developer impact. We wanted to handle the majority of our complex relational data models supported by our application. Application devs could then focus on building exciting new features in Figma instead of refactoring large parts of of our code base. I'll riff on this a little bit because I think this is emphasizing the point I was making. It's almost like they hired a mini database startup within their company in order to enable devs to work the way they expect. Because even Figma knows that the devs at Figma shouldn't have to care about these things. So they formed this team to build such that those people don't have to care about these things anymore. Scale out transparently. As we scale in the future, we don't want to have to make additional changes at the application layer. This means that after any initial upfront work to make a table compatible, future scale-outs should be transparent to our product teams. Skip expensive backfills. We avoided solutions that involve backfilling large tables or every table at Figma. Given the size of our tables and Postgres throughput constraints, these backfills would have taken months. That's something I hadn't even thought of here, just due to the terabytes of data they have because they have so much data they're storing in Postgres. Because it's not as simple of like, user has these properties and has these relationships. The nature of Figma's product and the complexity of the canvas, and the chances are that they're storing all of that data in their database through Postgres. That's just hilarious amounts of just raw text and other data being stored in Postgres. Backfilling that and transferring that out, I don't even want to think about how long that would take. They also talk here about making incremental progress. We identified approaches that could be rolled out incrementally as we de-risk major production changes. This reduced the risk of major outages, and it allowed the databases teams to maintain Figma's reliability throughout the migration. Again, one of those really difficult challenges that we have to worry about when we're building a product people use is how do we make a massive change like this such that every step along the way, if it fails for reasons we don't know yet, we can take a step back and make sure the product still works for our users and that our developers aren't blocked. Huge thing to think about, and migrations can be chaotic in this way. Oh boy, this is a fun one. Avoiding a one-way migration. Same general gist is my guess here. We maintained the ability to roll back even after a physical sharding operation is completed. This reduced the risk of being stuck in a bad state when unknown unknowns occur. This is very similar to what I was saying before, where we can't necessarily actually know what does and doesn't work. As such, we can make our best guesses, but we need to make sure we can also roll back if our guesses were wrong. And all of your migrations, all of your designs around these things should be focused on that. I have a philosophy I talk a lot about, or used to talk a lot about, don't quite as much anymore. I used to bring this up during the unit testing debates, where my focus was never building guardrails that keep you from falling over. Because no matter how many guardrails you build in your application, no matter how much work you put in to make it less likely somebody falls over, someone's going to fall, no matter what the fuck you do. As such, having a safety net to fall into so that you can recover and try again will always be more important than the quality of your guardrails. The things that keep you from fucking up will never, ever, ever be as important as the thing that helps you bounce back when a fuck up happens. Because as they say here, unknown and unknowns will occur. You can never know all of the ways something will fail until you've hit all of the ways that they fail. And you'll never know all of them. You'll just know the ones that you've run into or other people have run into and documented. As such, you should have a way to bounce back if you were wrong and something failed in a way you did not expect. Maintaining strong data consistency is also a key point for them. We wanted to avoid complex solutions like double writes that are challenging to implement without taking downtime or compromising on consistency. We also wanted a solution that would allow us to scale out with near zero downtime. I think double writes aren't the biggest deal. I think you can implement those in a lot of ways that are totally scalable, even if it's just a Postgres extension that mirrors all of the queries to somewhere else. Yeah, play to our strengths. Since we're operating under tight deadline pressure, whenever possible, we favored approaches that could be rolled out incrementally on our fastest growing tables. We aim to leverage existing expertise as well as technologies. Also very fair. So let's take a look at their options. There are many popular open source and managed solutions for horizontally sharded databases that are compatible with Postgres or MySQL. During our evaluation, we explored Cockroach, TIDB, Spanner, and Vitesse. However, switching to any of these alternative databases would have required a complex data migration to ensure consistency and reliability across two different database stores. Yes, this is the hard part. Could they have switched to MySQL and Vitesse and had a good time? Sure. In fact, Uber Postgres to MySQL. Uber, back in 2016, did the same thing, where they were on Postgres and they moved to MySQL because they wanted to get these same scaling behaviors. The issues they had with Postgres were things like inefficient architecture for writes, inefficient data replication, issues with table corruption, poor replica and VCC support, difficulty upgrading to newer releases. Does Vitesse come up in here? It doesn't even come up in here. Specifically, in many of the cases we previously used Postgres, we now use Schemaless, a novel database sharding layer built on top of MySQL. Interesting stuff. I've seen a surprising number of places move to MySQL, as crazy as that might sound, because it does scale a bit better. But moving to a different database technology is not easy. Moving from a standard Postgres install to MySQL plus Vitesse, especially if you're doing crazy stuff like arrays or like matching on JSON blobs. Don't even want to think about that. Additionally, over the past few years, we've developed a lot of expertise on how to reliably and performantly run RDS Postgres in-house. Again, How insane is it that Figma had to scale up a database team and build all of this knowledge internally in order to solve these problems? It's kind of crazy. While migrating, we would have had to rebuild our domain expertise from scratch. Given our very aggressive growth rate, we had only months of runway remaining. De-risking an entirely new storage layer and completing an end-to-end migration of our most business-critical use cases would have been extremely risky, unnecessary timelines. We favored the known low-risk solutions over potentially easier options with much higher uncertainty, where we had less control over the outcome. This is a very good point. The fact that they had a somewhat known, very scary timeline to get something out, I think they should have had multiple solutions in parallel going to solve that. But regardless, picking the one that is within their best understanding is entirely reasonable. NoSQL databases are another common scalable by default solution that companies adopt as they grow. However, we have a very complex relational data model built on top of our current Postgres architecture, and NoSQL APIs don't offer this kind of versatility. I don't even want to think about how you would implement something like Figma in Mongo. The thought makes me sick. I know. Just like the complexity of users plus orgs plus projects plus invites plus all of the different nesting that can exist. I am very thankful I'm not building Figma, and I'm certainly thankful I'm not doing it in Mongo. We wanted to keep our engineers focused on shipping great features and building new products instead of rewriting almost our entire backend app. NoSQL wasn't a viable solution. Very fair. Given these trade-offs, we began to explore building a horizontally sharded solution on top of our existing vertically partitioned RDS Postgres infra. It didn't make sense for our small team to re-implement a generic horizontally sharded relational DB in-house. I should probably quickly say what horizontal sharding is for those who aren't deep in the nerdiness of databases stuff. And as much as you're making fun of how I pronounce shard, it is what it is. Instead of the vertical solution where different tables get their own databases, once you hit a certain threshold in a given table, one table can be sharded across multiple database instances. So different users could be on different servers for the user profile row. That is what the horizontal sharding means, is each row could be split across multiple databases instead. In doing this, they would be competing with tools built by the likes of large open source communities and dedicated database vendors. However, because we were tailoring horizontal sharding to Figma's specific architecture, we could get away with providing a much smaller feature set. For example, we chose not to support atomic cross-shard transactions because we could work around cross-shard transaction failures. We picked a co-location strategy that minimized the changes required at the application layer. This allowed us to support a subset of Postgres that was compatible with the majority of our product logic. We also were able to easily maintain backwards compatibility between sharded and unsharded Postgres. If we ran into unknown unknowns, we could easily roll back to unsharded Postgres. This is a very fair approach. It's also important to know that once you create these sharding solutions, you do lose some of the functionality that exists within the database. For example, if you were using MySQL on top of Vitesse, you didn't have foreign key constraints for a while because we didn't really have foreign keys. The idea of when you delete a user, all of their posts get deleted too, that was a manual cleanup thing you'd have to do when you were using Vitesse, because for Vitesse to perform, in order to shard in these ways, you have to make the queries to get all the data yourself, rather than using links and explicit behaviors built into those links. They've since added foreign keys to Vitesse, and the things they did to make that work are insane. But the fact that we have to think about that at all says a lot about how hard it is to do these things and to make a SQL database with all of these relational behaviors scale. Let's talk about the path to horizontal sharding. Even with the narrower requirements, we knew horizontal sharding would be our largest and most complex database project to date. That's putting it lightly. The amount of work that went into building these things in every ecosystem is absurd. Just like Vitesse was the product of YouTube and GitHub's need to scale their databases, and it was so much effort over time. It's also one of the first big Golang projects, funny enough. Luckily, our incremental scaling approach over the past few years bought us the runway to make this investment. In late 2022, we set out to unlock nearly infinite database scalability as well as horizontal sharding, the process of breaking up a single table or a group of tables and splitting the data across multiple physical database instances was the key. I thought I was taking too long to define horizontal sharding. They waited till even longer, so I'll take the W. Once a table is horizontally sharded at the application layer, it could support any number of shards at the physical layer. We can always scale out further by simply running a physical shard split. These operations happen transparently in the background with minimal downtime and no application level changes required. This capability would allow us to stay ahead of our remaining database scaling bottlenecks, removing one of the last major scaling challenges for Figma. If vertical partitioning lets us accelerate to highway speeds, horizontal sharding could remove our speed limits and just let us fly. Very good stuff. And I like that framing here of the acceleration with the vertical partitions, which let them go way further. Now the limits are just gone. Really important distinction there, where the vertical stuff gave them a lot of free room to fix some shit, but also was just additional runway. It wasn't the final solution. Here is a nice little diagram. I wonder what tool they use to make these. Nice little diagram showing the difference here, where the user table is split on different tables, which can then be split even further from there. Horizontal sharding was an order of magnitude more complex than our previous scaling efforts. When a table is split across multiple physical databases, we lose many of the reliability and consistency properties that we take for granted in ACID SQL databases. For example, certain SQL queries can become inefficient or impossible to support. Application code must be updated to provide enough information to efficiently route queries to the correct shards wherever possible. Schema changes must be coordinated across all shards to ensure the databases stay in sync. Foreign keys and globally unique indexes can no longer be enforced by Postgres. Again, the foreign keys thing is very difficult here. In true global uniqueness, when you don't know between the different boxes, total mess. Transactions now span multiple shards, meaning Postgres can no longer be used to enforce transactionality. It is now possible that writes to some database will succeed while others fail. Care must be taken to ensure product logic is resilient to these partial commit failures. Imagine moving a team between two orgs only to find half their data was missing. Really good example. We knew that achieving full horizontal sharding would be a multi-year effort. We needed to de-risk the project as much as possible while delivering incremental value. Our first goal was to shard a relatively simple but very high traffic table in production as soon as possible. This would prove the viability of horizontal sharding while also extending our runway on our most loaded database. We could then continue building additional features as we worked to shard more complex groups of tables. Even the simplest possible feature set was still a significant undertaking. End to end, it took our team roughly 9 months to shard our first table. That's like massive like props to them for succeeding with this. The fact that they had to is still very frustrating to me. Our unique approach. Our horizontal sharding work built on what many others do, with some unusual design choices. Here are a few highlights. Colos. We horizontally sharded groups of related tables into co-locations, which we affectionately call colos, which share the same sharding key and physical sharding layout. This provided a friendly abstraction for devs to interact with horizontally sharded tables. Logical sharding. We separated the concept of logical sharding at the application layer from physical sharding at the Postgres layer. We leveraged views to perform a safer and lower cost logical sharding rollout before we executed a riskier distributed physical failover. Interesting. DB proxy query engine. We built a DB proxy service that intercepts SQL queries generated by our application layer and dynamically route queries to various Postgres databases. DB proxy includes a query engine capable of parsing and executing complex horizontally sharded queries. DB proxy also allowed us to implement features like dynamic load shedding and request hedging. Do you guys understand how crazy it is that they have to do this? That they have to build their own SQL query layer where they're taking in a query, they're parsing it, they're deciding which Postgres instances it should go to and which parts which Postgres instances should go to and splitting it up accordingly, pulling it all together and then sending you the bundled together result. This is chaos that they had to basically invent their own Postgres on top of Postgres to route their Postgres to the right Postgres. Whew. Shadow application readiness. We added a shadow application readiness framework capable of predicting how live production traffic would behave under different potential sharding keys. This gave product teams a clear picture of what application logic needed to be refactored or removed to prepare the application for horizontal sharding. Also an important thing to make a proper shadow solution. Like the amount of times I run into issues with high traffic stuff, like when I worked at Twitch, just simulating realistic user behaviors to make sure these things scale is insane. Full logic replications. We avoided having to implement filtered logical replication, where only a subset of data is copied to each shard. Instead, we copied over the entire data set and then only allow reads and writes to the subset of data belonging to a given shard. Interesting. Our sharding implementation. One of the most important design decisions in horizontal sharding is which shard key to use. Horizontal sharding adds many data model constraints that revolve around the shard key. For example, most queries need to include the shard key so that the request can be routed to the right shard. So again, if we go back to the example here where users is split 1 to 50, 51 to 100, 101 to 150, 151 to 200, when I make a query, how is it known which of these boxes it should go to? What happens if user 47 is deleted? Does it get filled with the next new user, or is there now a blank spot in this shard forever? How do we route these things? How do we update these things? How do we get to them from the application layer? It's not as simple as just give me this ID and then the database gives you the response. These things are harder, and you often need to have a different solution to actually get to the right shard. Certain database constraints, like foreign keys, only work when the foreign key is the sharding key. The shard key also needs to distribute data evenly across all shards to avoid hotspots that cause reliability issues or impact scalability. Also a really important piece. And a good point here, which is that Figma lives in the browser and has a big collaborative model where a lot of users are doing things in parallel. So how do you make sure when two users are doing specific things and maybe touching the same thing at the same time that we get the result to the right shard and it's the right, most up-to-date result? These things are already hard with a transactional database. They get way harder when you throw away the transactional reliability. We considered using the same sharding key for every table, but there was no single good candidate in our existing data model. To add a unified sharding key, we would have to have created a composite key, add the column to every table's schema, run an expensive backfill to populate it, and then substantially refactor the existing product logic. Instead, we tailored our approach to Figma's unique data model and selected a handful of sharding keys like user ID, file ID, or org ID. Almost every table at Figma could be sharded using one of these keys. We introduced the concept of colos, which provide a friendly abstraction for product developers. Tables within a colo support cross-table joins and full transactions when restricted to a single sharding key. Most application code already interacted with the database this way, which minimized the work required by application devs to make a table ready for horizontal sharding. Interesting. So the way they structured things was that users 1 through 100 would have their favorite tables or whatever other thing is relied on with users within the same shard. So the horizontal sharding is actually keeping vertical concerns aligned. Very, very interesting to do it this way. And here with files, the file comments are in the same table as files, so you can efficiently query once you get into this shard. Once we pick our sharding key, we need to ensure that there would be an even distribution of data across all backend databases. Unfortunately, many of the sharding keys that we had picked use auto-incrementing or Snowflake timestamp prefix IDs. This would have resulted in significant hotspots where a single shard contained the majority of our data. We explored migrating to more randomized IDs, but this required an expensive and time-consuming data migration. Instead, we decided to use the hash of the sharding key for routing. Interesting. If you're struggling to follow, the TLDR of this is that if you were to do this incrementally like we have here, how many of the first 100 users on Figma are still using Figma? This shard might just be doing nothing. Where if users 175 to 200 were all at a design firm signing up at the same time, this shard might have an insane amount of traffic. So how do you shard in a way where the traffic is being split more fairly? Because there will always be, in reality, hotspots. If 10 users sign up at the same time, or one user that's at a big company spins up 5 new apps at the same time, if those things are being sharded such that they're all in the same vertical, or they're all in the same shard, that shard's going to get overloaded fast. The best solution here is ideally just randomizing it, because randomizing which data goes where significantly decreases the chances of these power users ending up in the same place, because we no longer are relying on over time given hotspots in reality applying to your sharding methodology. So it's going random might sound stupid, but it's actually a really good solution here. As long as we picked a sufficiently random hash function, we would ensure a uniform distribution of data. One downside of this is that range scans on shard keys are less efficient, since sequential keys will be hashed to different database shards. However, this query pattern is not common in our codebase, so it was a trade-off we were willing to live with. But this means if you wanted to specifically select from user 105 to user 200, this would make that really inefficient, but it's very rare you would want to do that. A logical solution. To de-risk the horizontal sharding rollout, we wanted to isolate the process of preparing a table at the application layer from the physical process of running a shard split. To do this, we separated logical sharding from physical sharding. We could then decouple the two parts of our migration to implement and de-risk them independently. Logical sharding gave us confidence in our serving stack with a low-risk, percentage-based rollout. Rolling back logical sharding when we found bugs was a simple configuration change. Rolling back a physical shard operation is possible, but requires more complex coordination to ensure data consistency. Also very interesting to handle the sharding on the application layer to make sure it works first before doing it on the infra and then having everything break. Interesting strat. Haven't seen this done before, but makes sense for where they were at. Once a table is logically sharded, all reads and writes will act as if the table is already horizontally sharded. From a reliability, latency, and consistency perspective, we appear to be horizontally sharded, even though the data is still physically located on a single database host. When we are confident that logical sharding is working as expected, we then perform the physical sharding operation. This is the process of copying the data from a single DB, sharing it across multiple backends, then rerouting read and write traffic through those new databases. I'm curious how they had to have done parallel writes for this at some point, right? Because they can have multiple logical shards in one physical, so if they just made all the logical shards initially to test it and they started splitting those across, that makes sense. The query engine that could. To support horizontal sharding, we had to significantly re-architect our backend stack. Initially, our application service talked directly to our connection pooling layer, PG Bouncer. However, horizontally sharding required much more sophisticated query parsing, planning, and execution. To support this, we built out a new Golang service, DB Proxy. Go continues winning. Also, I love they call it Golang. Everybody gets mad when you do that, but it's the only way to be clear, especially when writing stuff like this. DB Proxy sits behind the application layer in PG Bouncer. It includes logic for load shedding, improved observability, transaction support, database topology management, and a lightweight query engine. Again, the fact they have to build things like this is insane. It's cool that they did, and I'm loving reading this, but holy shit. I know they have to use Figma for these things, but this could have been an Excalidraw. Ugh. Anyways, the query engine is the heart of DB Proxy. Its main components are as follows. The query parser, which reads SQL sent by the application and transforms it into an abstract syntax tree. They're turning SQL into ASTs. A logical planner parses the AST and extracts the query type, insert, update, etc., and logical shard IDs from the query plan. And then the third part, a physical planner, which maps the query from logical shard IDs to a physical database. It rewrites queries to execute on the appropriate physical shard. So we have this query, which is select star from table where shard keys X and other columns Y. So we have this additional info. This is the parsed part. And now we're going to plan. So we have this plan. It's a logical select from a single shard query with this ID. And now we have this plan architected in the physical select plan, which is actually sending it to the database, and it's going to that shard because it has shard 4 is the thing it's going to get. All makes sense so far. Think of scatter gather like a database-wide game of hide and seek. You send out your query to every shard, scatter, then piece together the answers for each, gather. Fun, but overdo it and your speedy database starts feeling more like a snail. Yeah, you have to go through everything to find something. You end up with a performance issue at a very different place than Postgres. Some queries are relatively easy to implement in a horizontally sharded world. For example, single shard queries are filtered to a single shard key. Our query engine just needs to extract the shard key and route the query to the appropriate physical database. We can push down the complexity of the query execution into Postgres. However, if the query is missing a sharding key, our query engine has to perform a more complex scatter gather. In this case, we need to fan out the query to all shards and aggregate back the results. In some cases, like complex aggregations, joins, and nested SQL, the scatter gather can be very complex to implement. Additionally, having too many scatter gathers would impact horizontal database sharding scalability. Because the query has to touch every single DB, each scatter gather contributes the same amount of load as it would have if the databases were unsharded. Yep. Once you're scatter gathering through all the DBs, you're in the exact same place. If every request requires every database to be hit, doesn't matter if you have one or a bunch. Yep. Again, their diagrams are really on point for this. If we supported full SQL compatibility, our DB proxy service would have begun to look a lot like the Postgres database query engine. Yeah, they basically would have rebuilt Postgres if they went any further. We wanted to simplify our API to minimize DB proxy's complexity while also reducing the work required for our application developers, who would have to rewrite any unsupported queries. To determine the right subset, we built out a shadow planning framework, which allowed users to determine potential sharding schemes for their tables and then run shadow the logical planning phase on top of live production traffic. We logged the queries and associated query plans to a Snowflake DB where we could run offline analysis. From this data, we picked a query language that supported the most common 90% of queries, but avoided the worst case complexity in our query engine. For example, all range scans and point queries are allowed, but joins are only allowed when joining two tables in the same colo, and the join is on the sharding key. Interesting. They allow for scans, but they don't allow for joins unless they're on the same key. This is something you can only learn from doing this data analysis, and this is one of the strongest arguments so far for why they should be building this themselves instead of using an existing solution, because they did all this analysis, they found which things they do and don't use the most, and they built their implementation here around those limitations. And I would imagine a lot of places use joins in all sorts of crazy ways. Like any data processing is going to need joins way more than they need range scans, probably. A view of the future. We then needed to figure out how to encapsulate our logical shards. We explored partitioning the data using separate Postgres databases or Postgres schemas. Unfortunately, this would have required physical data changes where we logically sharded the app, which was just as complex as doing the physical shard split. Instead, we chose to represent our shards with Postgres views. This is a pretty cool and common hack. For those who aren't already familiar, Postgres has the ability to query things that aren't part of the Postgres data layer. And I've seen more and more people who are building Postgres scaling stuff, dropping the Postgres storage layer in favor of using Postgres as a view layer to another storage solution. We could create multiple views per table, each corresponding to the subset of data in a given shard. This would look like the following. Create view table shard 1 as select star from table where hash shard greater than or equal to min shard range and the shard key is less than max. All reads and writes of the table would be sent through these views. Yeah, interesting to create a view that is bound in that way. By creating sharded views on top of existing unsharded physical databases, we could logically shard before we performed any risky physical reshard operations. It's actually a really good point too. By doing this through the views, they don't have to do anything to the database, and they can still know, for the most part, is this working or not? What are the characteristics of the new state of things? It is really interesting that they're using views as a way to test these changes almost, and then they can rebind the view to the actual shards later on. I actually really like the strategy. Each view is accessed via its own sharded connection pooler service. The connection pooler still points to the unsharded physical instance, which gives the appearance of being sharded. We were able to de-risk the rollout of sharded reads and writes gradually via feature flags in the query engine, and roll back at any time within seconds just by rerouting traffic back to the main table. By the time we ran our first reshard, we were confident in the safety of the sharded topology. This is a really cool thing. I actually really like the idea of using views to do that logical sharding to test this all works. They did a great job of de-risking and like getting these things out. And the idea of feature flags being used to change where we're routing is really cool. Really cool stuff. Of course, relying on views also introduced additional risks. Views added a performance overhead and in some cases could fundamentally change how the Postgres query planner optimized queries. If you're not familiar, Postgres has the query planner built in where it will analyze a query and then make decisions about how it's going to approach that query to be as optimal as possible. If you're using views, its understanding of how it can optimize things is not as strong and you could run into issues. To validate the approach, we collected a query corpus of sanitized production queries and ran load tests with and without views. We were able to confirm that views would only add a minimal performance overhead in most cases and less than 10% in the worst cases. We also built out a shadow reads framework, which could send all live read traffic through views, comparing the performance and correctness of views versus non-view queries. We were then able to confirm that views were a viable solution with minimal performance impact. Again, yes, views add some performance impact, but it seems like most of the time it's not particularly bad. If less than 10% in the worst cases for Figma, for most places, it's going to be totally fine. I think that views are almost certainly going to be the future of Postgres for these reasons. Tackling our topology. To perform query routing, DB proxy has to understand the topology of our tables and physical databases. Because we had separated the concept of logical versus physical sharding, we needed a way to represent these abstractions within our topology. For example, we need to be able to map a table to its shard key, which would be users and user ID respectively. Similarly, we need to be able to map a logical shard ID, like 1, 2, 3, to the appropriate logical and physical databases. With vertical partitioning, we relied on a simple hard-coded configuration file that mapped tables to their partitions. If you're looking for user, here's where the user table is, go there. However, as we moved towards horizontal sharding, we required something more sophisticated. Our topology would change dynamically during shard splits, and DB proxy needed to quickly update its state to avoid routing requests to the wrong database. Because every change to the topology is backwards compatible, these changes are never in the critical path for our site. We built out a database topology that encapsulated our complex horizontal sharding metadata and could deliver real-time updates in under a second. Interesting, under a second's their benchmark. I guess for their product that does make sense, but it's that's a really high throughput. So there's a rough sketch of how they handle this proxy layer. They have the topology library, which knows what is where. They have the config file, which is in S3, and then the notification bus that goes to their etc. dump. That's what I'm assuming etcd is. Cool. Having a separate logical and physical topology allowed us to also simplify some of our database management. For example, in our non-production environments, we can keep the same logical topology as production, but serve the data from many fewer physical databases. This saves costs and reduces complexity without having too many changes across environments. This is another really important piece. Meaningfully replicating things locally is obnoxious. Really hard to do in dev. And it's dope that they considered that, and through these logical view layers, they're able to let you have one database locally when you're doing dev work, and everything still behaves identically. It might be slightly faster because it's one thing, but this is a really good point that I hadn't thought of, is the local reproducibility, which is dope. Also, I was wrong. etcd or etcd is a KV store used by Kubernetes, so this is likely part of how they're configuring the infrastructure itself. The topology library also allowed us to enforce invariance across our topology, like every shard ID should be mapped to exactly one physical DB. These were critical to maintain the correctness of our systems as we built our horizontal shards. Checks out. The physical sharding operation. Once a table is ready for sharding, the last step is the physical failover from unsharded to sharded DBs. We were able to reuse much of the same logic for the horizontal sharding, but there were a few notable differences. Instead of moving data from one database to one database, we were going from one database to n databases. We needed to make sure the failover process was resilient to new failure modes, while the sharding operation could succeed on only a subset of our databases. Still, many of the riskiest components had already been de-risked during the vertical partitioning. We were able to move much faster towards our first physical sharding operations than we would have otherwise been able to. We've come a long way. When we started this journey, we knew that horizontal sharding would be a multi-year investment into Figma's future scalability. We showed our first horizontally sharded table in September of last year. We successfully failed over with only 10 seconds of partial availability on database primaries and no availability impact on replica. We saw no regression in latency or availability after sharding. Since then, we've been tackling relatively simple shards from our highest write rate databases. This year, we'll shard increasingly complex databases, which have dozens of tables and thousands of code call sites. To remove our last scaling limits and truly take flight, we will need to horizontally shard every table at Figma. A fully horizontally sharded world would bring many other benefits: improved reliability, cost savings, and even developer velocity. Along the way, we'll need to solve all of the following problems. For horizontally sharded schema updates, oh god, I hadn't even thought of that. Doing a schema update across the shards. Globally unique ID generation for horizontally sharded primary keys. Atomic cross-shard transactions for business-critical use cases. This is, again, like making sure users don't have any way to do things out of order, guaranteeing order. That when I make a transaction, like we'll use literal transaction, like a bank transaction. If I am adding money to my bank and then something else is withdrawing money from my bank and I added the money first, it's really important that me adding the money comes first and then withdrawing it comes second, especially if the end state is just the number that we put in. If I start at $10, they withdraw $5, and then I add $5. My end number is 15. Their end number is 5. The truth end number is 10. But depending on which goes first or second, you might end up with 15 or 5 as the value in the database. Doing these things right is really hard. Distributed globally unique indexes are an important piece too. Currently, unique indexes are only supported on indexes that include the sharding key. Again, if they're all within one shard, you can still do like unique indexing, but you have no idea if a certain user ID doesn't exist anywhere else. You only know it doesn't exist within that shard. An ORM model that increases developer velocity and is seamlessly compatible with horizontal sharding. Good luck. And then fully automated reshard operations that can run shard splits with the click of a button. Ideally, you don't even have to click a button to do that. Ideally, the shards handle themselves like they do in other systems, but I get why you'd want it to be a manual process with the chaos you've gone through. Once we've bought ourselves sufficient runway, we'll also reassess our original approach of in-house RDS horizontal sharding. We started this journey 18 months ago with extremely tight timeline pressure. New SQL stores have continued to evolve and mature. We will finally have the bandwidth to reevaluate the trade-offs of continuing down our current path versus switching to an open source or managed solution. We've made a lot of exciting progress on our horizontal sharding journey, but our challenges are just beginning. Stay tuned for deep dives, yada yada. They're telling you that they want to hire, which makes sense. If they're doing cool stuff like this, might be a good place to work if you're into these types of things. I want to dive onto this though, because it seems like what happened here was a pretty common, I don't have a good term for this, but it's kind of like tech debt waterfalling, where you run into more and more like, we need to solve this problem right now, our hair is on fire. And you find what seems like the most immediate solution. And then you realize something else gets broken, so you have to fix that. And then you just do that over and over again until all of a sudden you're reinventing Postgres. And that's a bit of what I see here. As much as people hate outsourcing these things, when you do it, that treadmill of like chaotic looping, at the very least, is outsourced somewhere else. I hate that anyone had to do this. And I honestly feel both admiration and sympathy to the engineers that had this chaotic problem and insane timeline thrown on them. Massive respect. They did a great job. This article was phenomenal. And as much as I wish they could have avoided this in the first place, I understand why they did it. Let me know what you guys think in the comments. I think this was a fun one. Until next time, peace nerds.